Hello, I'm Nick Romeo, and I'm gonna work through a related rates problem with this. So, the question starts as, oil is leaking from the pipeline on a surface of a lake that forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. So, when I get a rate like this, I usually just write, what is it, dv of dt, that's the volume, and I just make it equal to 2,000. I just do centimeters cubed per minute. And that just makes it easier for me later on in the problem when I gotta go, okay, what am I looking at? Okay, I know what dv of dt is, so it's a lot easier for me to just mentally know what everything is while I read through the problem, so I can just get it out of the way and go as quick as possible. Next, it says the oil slick takes the form of a right circular cylinder with both the radius and height changing with time. So it's just telling us it's going to be in the shape of a cylinder, which I drew in here. I like drawing one just because it makes it a little easier for me to see visually. If I want to change stuff in the cylinder, I can. I could add stuff. I could erase. I just like making shapes. It makes it a little easier to know where I'm at. Okay, so let's get to the first part. So the first part says, an instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters. The radius is increasing at a rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? So let's pick apart this first part and see what we're given and what we need to find. So first off, it says at an instant when the radius of the oil slick is 100 centimeters. So right there, it's telling us the radius equals 100 centimeters for this part. And the height is 0.5 centimeters. So I write them out, makes it easier for me. I know where they are, know what I'm looking at. So then it says the radius is increasing at a rate of 2.5 centimeters per minute. So there, it says the rate. So this is telling me that this 2.5 is dr dt because it's the rate of the radius in respect to time. So I write that down again so I know what variables I have. And then now it's asking for at the instant when the rate of change of the height of the oil slick, or it's asking for what the rate of change is. So what we don't know is the height. It's asking for the rate of change of the height for dh of dt. That is the unknown of this question. So first part that we're going to need to do is take the derivative of this equation that they gave us. So I'll write it out. What we have to do next is take the derivative of this equation. So this left side, derivative of just v, is dv over dt. That's all we get over there. Then this side, the pi r squared h, we have to do product rule. So how would we do the product rule of this? We have to bring the 2 over, so it would be 2 pi r. Because we took the derivative of r, it's dr dt, and the h is still there. So the second part of the derivative is pretty easy because it's just h, so it would be pi r squared, and derivative of h is just dh over dt. So that's the derivative we have now. So now the next step is look back up into what we wrote earlier and see what we could plug in. So I see I have a dv dt and it's 2,000 centimeters. So I can plug in a 2,000 centimeter, or not centimeters, but I can plug in a 2,000 right there. So next I look, okay, the radius is 100. So I could go 2 pi, just 100. And then do I have a dr dt? I do. It's 2.5. And then do I have any h's? I do have an h. So it's 0.5. Okay. Then I have a pi. Do I have a radius? I do have a radius. It's 100 squared. And do I have a dh dt? No. That's what I'm trying to find. So we have all our numbers plugged in. We have our one variable. So all I need to do is calculate all this out. So this right here is 250 pi And this over here is 10,000 pi dH dt. So next, pretty simple, easy algebra. So once you calculate all this out, you'll get dH dt equals 0.39 centimeters per minute. All right, so part B says, a recovery device arrives on scene and begins removing oil. The rate at which oil is being removed is R of t equals 400 radical t cubic centimeters per minute, where t is the time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time t when the oil slick reaches its maximum volume. So, our first step is we got to take dV of dt equaling 2,000. We got to subtract that by 400 pi of t. The reason why we need this formula now is we're saying the rate at which the oil is going into the slick, which is here. This is the rate in. And this is the rate of the machine, the recovery device we just got clarified of. So this is the rate out. So we can look at this and we have a new equation. So we can start plugging in stuff for t and playing around. So we do dV of dt equaling 2,000 minus 400. If we plug in 25 for t, it makes this whole thing 0, because it would be dV dt equals 2,000 minus of 25. So the square root of 25 is 5. So 5 times 400 is 2,000. So dV of dt when t is equal to 25 equals 0. So now let's take a look back at the question. So it's asking for time t when the oil slick reaches its maximum volume. So we found when dV of dt equals 0. So because we found that it equals 0, we now know that that's the maximum, because if the rate out is equal to the rate in, then that means it's at its max, because every interval after 25 now is going to give more out than going in. So after 25 minutes, it'll start declining because the rate in is not increasing at all, but the rate out is. So 25 would be the answer to this question. So let's take a look at the last part of the question. So part C. By the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already been leaked. Write down but not evaluate an expression involving the integral that gives the volume of an oil at that time found in part B. So it says the device began removing oil at 60,000 cubic centimeters. So we know that before the machine even got there, it was already at 60,000. So I'm just going to say the expression of the volume is just V. I'm just going to say it's V. This really isn't anything, but it has to be 60,000 because that's what it was. That's how much oil was leaked before the recovery device even got there. All right, so we got to equal to 60,000. So what we now need is the actual integral part. So we could add this to the integral because that's the starting out point pretty much. So it says use the time found in part B. So we know it has to go up to 25 because that's the answer we had in part B and also we get from part B the inside because that's how we got the 25. So it's as simple as that. Just nice, and it's only asking for the expression. We don't have to solve anything. So yeah, this would be what the volume would be because it's the rate that's going in minus the recovery device. That's what it has to be from 0 to 25 because that was before they got there. And now this is adding when they get there, still it goes till 25 minutes. So you still need the RFT. So yeah, that's about it. Thanks for watching. Hopefully I could help. I know I'm probably not the best. I tried trying to tell some tips. I just like writing everything down. So yeah, thanks for watching, everyone.